The next form of alternative energy that we are going to discuss is wave power. All right, wave power can also be called tidal power. Sometimes they're both used synonymously, but they are different. All right, tidal power, typically we imagine giant turbines under the water harnessing the power of tides. With wave power, though, the idea is that we have these things called oscillating water columns, all right? And so when waves come into shore, they have peaks and troughs, all right? So this difference in the elevation of the water can cause, if you see the apparatus there that's on your page, air to be pushed in and out of this little column. And when that happens, and if you direct it properly, all right, it'll cause a fan to, go back to rotate, and so that rotating fan will help to generate power. So that's the idea there, right? We go from the mechanical energy of the water, all right? So the kinetic energy of the water, you can say, transfers to the kinetic energy of the air, all right? And this goes to the kinetic energy, mechanical energy of the turbine. And as always, from here, we go to electricity. So the way that we can show, all right, how much power is developed by a wave is to consider actually a square wave. It's really the easiest way to conceive of this, all right? So we have this square wave. What we're going to say here is that this height from the trough to the peak is 2a, and that makes sense because this little dashed line I've drawn here, this is the equilibrium position. We know that if we measure the height of the wave from the equilibrium position, that is what the amplitude is, okay? So if we consider this, though, from a point of view, all right, where we're thinking of it as a gravitational potential energy, okay, then what happens is that we can take this top little box off, I'm going to highlight it here, okay, that's above, all right, this equilibrium position, and we can put that down here, okay? So, I mean, this is, if we think about it, this would be the total amount of water that we care about, okay? And so if we look at this, the average height of this water above, we'll call this the reference height, h equals 0, okay? The average height of this over here is going to be halfway up, right? So what we see is that the average height, okay, the delta H here of the water, all right, in terms of gravitational potential energy, is going to be 1/2 A. If you're confused about why that is, ask me in class. I'll be happy to show you and go back through that. So we start out, we want to figure out how much gravitational potential energy is stored, all right, in these waves, in these square wave fronts. We're only going to consider one wavelength here, all right? So we know that potential energy is equal to mgh, our generalized formulation here that we have way back in mechanics. We've established, actually, here we go. We've established this right here, okay, that will be half the amplitude. And then the other piece that we would need here is the mass. So, since we're dealing with water here, we're going to be doing this density calculation again, all right? So let's start with, all right, the volume. The volume of water that we care about here, all right, if we do this calculation, will be equal to the length of the wavefront, all right, times the height here, all right, times the width here. So the height is 2 times the amplitude, and the width is half the wavelength. So your volume looks something like this. Okay? Obviously the 2.5 are going to cancel out, so we are left with this. So what this leads us to is that the mass is going to be equal to the density times the volume, and this is just the same as rho times A lambda L. Okay? When we substitute that in here, we get our potential energy stored in this wave as the following. We rho times A squared times G, excuse me. All right? Actually, here, we write it like this. Rho times A times lambda times L, okay, times G times 1/2
That's the whole thing. Substituting in for mass and for delta H. Now, if we consider, okay, that the power supplied by this water is just the rate at which the potential energy is converted per time, we get the following equation. And just square the amplitude here, right, times G, and this whole thing is over delta T. And we'll put the 2 down here as well, from the 1/2, okay? Now, we have to remember, all right, that this whole thing is happening over one wavelength, so delta T is going to be equal to the period. And if I put that in here, what we end up with, okay, is rho times a squared times L times G times lambda, all right, all over 2 times the period. And lambda over the period is the wave speed, okay? So, again, just one more substitution here. We end up with rho times a squared times G times V, and move the L over here, all right, all over 2 is equal to the power. And the way that we typically actually define power is it's going to be power per unit wavelength, excuse me, per unit length of wave front. So let me repeat this. This is power per unit length of wavefront. And so this final equation here looks something like the following. P over L equals rho times G times a squared times V all over 2. Again, just an approximation to tell us how much power can be developed by this wave. So that's the derivation, okay? Some example problems that you would have to solve for this, all right? Given, the amplitude of a wave, given the speed of the wave and the density, you have to calculate, all right, the amount of power that they would carry per meter, all right, of short wave. So again, this is just P over L. You get rho G amplitude squared times V all over 2. And when you substitute all of your values here, okay, we have the amplitude here, the density, and the speed, all right, we end up with 110 kilowatts per meter. Okay, make sure you substitute all those in and carry out the calculation. The power along a 2 kilometer stretch of beach, what we're looking for here, P is just to be equal to P over L times L. All right, this is the length of the wavefront that we're considering. So in this case, it's just 110 kilowatts per meter times 2,000 meters. We end up with 220 megawatts, okay? All right, there we go. Pretty unrealistic though as far as capturing all that power in terms of those oscillating air columns, but just trying to introduce you to this. Sorry, oscillating water columns, I think they're called. Okay. So, waves that are 6 meters high, that's incredibly high, with a 100-meter wave length, all right, roll into a beach at a rate of one every 5 seconds, okay? So, some ridiculous numbers here, all right? But let's just do the calculation and estimate the power of each meter of the wavefront. Good fun. Okay, so our amplitude is 6 meters. All right, the wavelength is 100 meters. All right, the frequency here, since it's one for every 5 seconds, all right, 1 all over 5 seconds here, 0.2 hertz. What else do we have here? We have the density we can assume for water is 1,000 kilograms per meter cubed. And we know acceleration of gravity we need. All right, so if we calculate this, and the one piece we need here is the wave speed, which is just going to be using our wave equation, lambda times f. So 100 meters times 0.02 hertz is going to give us 20 meters per second. And substitute all these values in here. Should give us a value of 1.2 megawatts per meter of wavefront.
Which is absolutely ridiculous. All right, that is very, very strong wave, though. I mean, waves do carry a lot of energy with them because of how much mass is in that water. And traveling at 20 meters a second, well, right there gives you an idea as to why tsunamis are so destructive. So that's it for wave power, okay? The next section will be on hydropower, and then that will be it for alternative energy.